Hello, and welcome to week 7, lecture 1, rotational inertia. So this is coming from chapter 9-2, and we'll talk about rotational inertia, Newton's second law for rotation. We'll do a couple sample problems, and then we'll talk about parallel axis theorem. Let's say you have the same long, thin rod, and you want to rotate it about 2 different axes. One along the rod itself, and then another perpendicular to the rod. You will find that rotating it along the rod is much easier than rotating it along an axis perpendicular to the rod. And this is because the rotational inertia is different in the 2 cases. So linear inertia or mass doesn't change values depending on the direction of motion, but rotational inertia depends on the axis of rotation. This is because it depends on how mass is distributed around the axis of rotation. In this first example, with rotating along the rod, the mass is close to the axis of rotation all along it. But in B, on average, the mass is very far away from the, there we go, from the axis of rotation. So here, all of the mass is concentrated along the axis of rotation, and here, most of the mass is concentrated away from the axis of rotation. More rotational inertia means there is more resistance to rotation about that axis. This is similar to a more massive object resisting acceleration. A larger rotational inertia resists rotation. Okay, so we have a mass rotating about the z-axis, which comes out of the screen. That's what this symbol means if you don't know. So we can look at the motion just in the xy plane. There is a force acting on the mass at this angle theta here. And that angle is coming from the radial line. We can find the tangential component of the force since we know that the component along the radial axis does not contribute to the rotation. So, because that's what we learned with torque, so looking at this force, there's a portion of it that will fall along the radial line, and then there's this perpendicular portion. And we learned that if it falls along the radial line, it doesn't cause any rotation. So we can take this perpendicular component instead, which we can also refer to as tangential because it's tangential to that circular motion that's occurring. So the net tangential force is the force times sine of the angle. And we know for Newton's second law that the tangential force is also equal to the mass times the tangential acceleration. So this relationship, this is just Newton's second law. We just have a subscript on it that we don't always, because we need to do that when we're talking about 2 different kinds of motion. And last week we learned that tangential acceleration is related to angular acceleration. By this relationship, tangential acceleration is equal to angular acceleration times the radius. So we can set these equations equal to each other, but plugging in this for the for the tangential acceleration. And then if we multiply both sides by r, we can get torque on the left side because, torque is RF sine theta. or RF of the angle between the radius and the force, which is what theta is in this case. So this times R gives us 4, and this is what we wind up with on the other side when we multiply by R another time. So we have the mass times the radius squared times the angular acceleration. So this equation is the rotational inertia of a single particle. It's given by I equals mr squared, where m is the mass, or the linear inertia, and r is the distance from the axis of rotation. The units of this are just kilograms times meter squared, nothing fancy. Inertia doesn't get its own unit. So now let's look at this situation. With 3 particles attached to the same object, all experiencing different forces. Each force applies a torque to each mass. So our masses, and then we have these different forces acting, and they're each applying a torque to our masses. So that means we have these equations for the torque of, or acting on each mass. The rotational inertia for each mass times its angular acceleration. But these masses are all part of the same object. That's what this is trying to show. They're all attached. And we also learned that angular acceleration throughout an entire rotating object is the same throughout. So that means that all of these angular accelerations are equal. And we can get the net torque, which is just like the net force, where you just sum up the torque acting on the total object. So in this case, we're finding it for the total object. And it is the rotational inertia for each mass times the acceleration, which we can simplify to the angular acceleration times the sum of each mass times the radius squared. And we said that at least for an individual particle, mass times the radius squared is the rotational inertia. So the sum of net external torque on a system is the rotational inertia of the system times the angular acceleration. And that is telling us that this sum of mr squared is the rotational inertia of the system. So now let's try this out ourselves. So we're going to do sample problem 9-2, and I'll read it to you first. 3 particles of masses, M1 equals 2.3 kilograms, M2 equals 3.2 kilograms, and M3 equals 1.5 kilograms, are connected by thin rods of negligible mass so that they lie at the vertices of a 3, 4, 5 right triangle in the XY plane. Find the rotational inertia about each of the 3 axes perpendicular to the XY plane passing through one of the particles. I'll go back through this when you can see the problem itself, or the figure. So yeah, let's work on this one. Okay, so here is my drawing of the situation. Oh, maybe I want to. So you can see we have our 3 masses at these different points on the XY plane. And the sides of our triangle are 3 meters, 4 meters, and 5 meters. And we want to find the rotational inertia if the axis of rotation acts perpendicular to the XY plane, but through each of the particles. So we want to compare what that would be. So we will just start with mass 1. Let's see. Mass 1. And we can get the distance between the the masses, the other masses in S1. And we'll just call those R1, 2, and that is 3 meters, just reading that off the figure. And R1, 3 is 4 meters. And let's just write these masses down so we don't forget them. Mass 2 is 3.2 kilograms, and mass 3 is 1.5 kilograms. Okay, so now we'll just use our equation for the rotational inertia. So 3.2 kilograms times 3 meters squared plus 1.5 kilograms times 4 meters squared. This gives us a rotational inertia of 52.8 kilogram meters squared. So that is the rotational inertia if it was just rotating like around the origin, but also around mass 1. Let's pick a different color and do for mass 2. And we'll just write the radii again. So from 2 to 1, it's still 3 meters. And from 2 to 3, it is 5 meters. And let's write mass 1 is 2.3 kilograms. And mass 3 is still 1.5 kilograms. Okay, same equation. So let's do rotational inertia, mass 2. And we have 2.3 kilograms times 3 meters squared plus 1.5 kilograms times 5 meters squared. And this one is 58.2. 58.2 kilogram meters squared for rotation about this point. And finally, we will do it about mass 3. And 3 to 1 is 4 meters, and 3 to 2 is 5 meters. And then I'll just write these masses. It just makes it easier. Let's see, except for I forgot what they were. Mass 1 is 2.3 kilograms, and mass 2 is 3.2 kilograms. Lots of switching up of the order of numbers here for us. Okay, yep. So same equation again, but just different variables we're plugging in. 2.3 kilograms times, sorry about that. Oh, there we go. Times 4 meters squared plus 3.2 kilograms times 5 meters squared. And this one is 116.8 kilogram meter squared. So that's much bigger than the other two. So that's interesting. I think one thing to think about like why moment of inertia, or sorry, that's another term for rotational inertia. I'll try not to say it though, because that's not what your textbook uses. But it makes sense that 3 rotating about 3 has the largest one because the other two masses are bigger than mass 3 and they're farther from mass 3. So we also have another sample problem about this same situation. So now we want to find the rotational inertia about an axis perpendicular to the plane, which is what we were doing before, but passing through the center of mass of the system. So this means we have to find the center of mass first. Oops. Okay, so let's remind ourselves of that. And actually, yeah. So the X position of the center of mass is 1 over the total mass times each mass times its X position, and then the Y version is the same, 1 over M, sum of M, Y. And the total mass, let's just get that out of the way. Total mass is 2.3 kilograms plus 3.2 kilograms plus 1.5 kilograms, giving us a total of 7 kilograms. 7 kilograms for capital M. And I'm just going to write what these coordinates are. Yeah, this one is 0 in X and 3 meters in Y. And this one is 4 meters in X and 0 in Y. And this one is just 0 and 0. Okay, so now let's find the X center of mass. So 1 over 7 kilograms times mass 1 is at the origin. So it doesn't get included in the mass times X or Y position part, but it is included in the overall mass. So let's ignore that one. And then mass 2, its X position is 0. So actually we're going to ignore that too. So it's just going to be mass 3, which is 1.5 kilograms, times 4 meters. And this is 0.86 meters. That's the X position. Let's do the Y position. Again, 1 over 7 kilograms. And this time it's only mass 2. Mass 2 is 3.2 kilograms times 3 meters. And this is 1.37 meters. So those are the positions of our center of mass. In order to find the moment of inertia about the center of mass, we need to figure out how far each of our masses is from that. So it's somewhere like this-ish. So we have R2, R1, and R3. Okay. So now let's figure out our distances from the center of mass. So for mass 1, that one's easy because it's at the origin and these are coming from the origin. So hey, look at that. Mass 1 is super easy. It's literally just like the coordinates of the center of mass. That's how far it is from it. And then mass 2 is on its X position is 0. So it's also the same distance in X from the center of mass, but then the Y position, we need to take its Y position and subtract the Y position of the center of mass, which is, I didn't write down, so we're not gonna. And then mass 3, so this one, the Y part is 0, so that part stays the same. So that one is 1.37 meters, but then the X, we have to take the difference. So we have 4 meters minus 0.86 meters. And then we can do R squared equals X squared plus Y squared for each of these. And we can just leave it as R squared, just like as a helpful tip, because the moment of rotational inertia is the sum of mr squared. So we can just leave it squared. But I didn't do that, so you're gonna have to bear with me while I do it really quickly. 0.86 squared plus 1.37 squared. So I'll just write it here. R1 squared equals 2.6. This is in meters squared. R2 squared is 0.86 squared plus 3 minus 1.37 squared. So that one is 3.4 meters squared. And finally, our 3 squared is 4 minus 0.86 whole thing squared plus 1.37 squared. That one is big, 11.7 meters squared. Okay, so looks like we have everything we need to find the moment of inertia, rotational inertia of the center of mass. So mass 1 is 2.3 kilograms, and it is 2.6 meters, or 2.6 meters squared for the radius. And then 3.2 kilograms times 3.4 meters squared, and 1.5 kilograms times 11.7 meters squared. So this gives us the rotational inertia of the center of mass is 34.5 kilogram meters squared. So that is much smaller than any of the other ones. So the lowest two were for I1 and I2. And that's still like, what was it? Almost 20, little less than 20 smaller. And this is to show that the rotational inertia through the center of mass of your object is the lowest rotational inertia. So one last thing I want to go back to the slides for. Okay, now the concept of parallel axis theorem. You can find the rotational inertia about an arbitrary axis parallel to the axis through the center of mass of a system with this relationship here. The rotational inertia of the center of mass plus the total mass of the system times h squared, where h is the distance from the rotation axis to the center of mass. So we can test this relationship right here on our situation that we just finished. And I think I even have room, a little bit of room on the page. So let's do that really quickly. So we will do this with, maybe just we'll compare to the rotational inertia through mass 1, which was 52.8 kilogram meters squared. And that means since that is going through this, our h, or the distance between that one axis of rotation and the axis through the center of mass, that's just r1. So we already found that, and we actually already found squared, so that's nice. H squared equals r1 squared, which is 2.6 meters squared. And we know the total mass is 7 kilograms. I think that's everything we need. I mean, technically, we don't need this. We're just comparing. So we say the rotational inertia through mass 1 is the rotational inertia through the center of mass plus total mass of the system times the distance between those two rotational axes. So this one is 34.5 kilogram meters squared plus 7 kilograms times 2.6 meters squared. And this is 52.8. 52.8 kilogram meters squared. So cool. Verified the parallel axis theorem there. So that's everything for this one. Have a good day.